there'll be, it seems, where are we now? 10, 11 questions? 11. I'm going to add 12 today. Okay, so 8 to 9 minutes a question, and we're going to be reviewing over the next 2 days. Okay, so after this. Okay, so today I would like to talk about maybe a couple more topics, and then we will get all the questions out and begin our review. I'll take any questions about that game plan. Your test next Tuesday. Okay, that's right. So, because the other class has their test on the 20th. That's why I was saying the 20th. So, and we may move that, by the way. So, because we only meet once a week in that class. Okay. Let's do this. Wait, do you not see this whole screen? That's interesting. Someone must have messed with the projector, but it's okay. Oh, maybe. Yeah. Let me ask you a question here about 5, 6, 4, and 6, 3. Are we experts at rotating volumes? Rotating. I have one expert.
No, I'm not an expert.
Not an expert. Who's really good at it? I have 3 people. 4. Who's completely befuddled by it?
I'm in between befuddled and good.
Okay, that's good. That's good. Okay, okay.
Befuddled, I just need
Okay.
to practice.
Should we practice some more?
Sure.
We'll start with that. Okay, so we'll go here. It's not going to give me any exercises. There we go. All right. So right now, this is the shell method. And rotating, let's just do number 6. Get us warmed up. And then, again, I have to, be honest here again. We've done a ton of these, okay? So I'm here as long as you feel like you need to be here for this problem and these types of problems. Again, on the exam, I'm going to give you a graph that looks like this, and I'll ask you to rotate it. In this case, is around the y-axis. We're talking about this rectangle here. Take this, rotate it around the y-axis. That creates a cylindrical shell with volume 2 pi x f of x. In this case, that's exactly what it is, 2 pi x f of x. It's not my goal to be tricky. Let's see what the answer is. What does Michelin give us? This is 6 minus x. There it is. On the interval 2 to 4. 6 minus x. On the interval 2 to 4. I'm rotating around the vertical axis right. Then you get something like that. Let's go back to the picture. Another question. That's the wrong one. Let me go to this one. So, I think that's right? Rotate it around the y-axis. You get something that looks like this. Yeah, I think so. Does everyone see that? What's the volume? How much can this hold? How much can this hold? So hopefully we see, going back here, 2 pi x. That's what that's. That's the ball game. They decided to pull out the minus sign. Again, that's just Maple being funny. Right? But it's the integral from 2 to 4 of 2 pi x times f of x. Again, that comes from taking the, look back at the diagram that this creates, right? But again, this creates this thing. There's a hole in there, right? And 2 pi x, f of x. It is at this point that I think we have to recognize that everyone's going to do this, okay? So again, 10 points. Everyone's going to do this. Please just get it right. So I think everyone's going to have this down perfect. Now it's just about doing this integral perfectly. And we get to the point where I have so much faith and confidence that I don't even have to do anything else. I can just go on to the next problem. But just in case, by the fundamental theorem of calculus, this is 3x squared minus 1/3 x to the 3rd evaluated from 2 to 4. Again, this is using the power rule. One of my great fears is that you all have fooled me tremendously about antiderivatives. That when the time comes, people will not know the antiderivative of secant squared. I'm worried, but I also have faith. Now, whether that faith is blind, I will find out. 48 minus 64 over 3 minus 12 minus 8 over 3. I'll take questions. Plug in 4 squared, 16 times 3, 48. 4 cubed is 64 over 3 is what it is. Plug in 2 squared, 4 times 3 is 12. 2 to the 3rd is 8, 8 over 3. And we subtract. Please, sir.
3x squared on the 3rd step.
Yes.
That's the antiderivative of
6x, that's correct. So you add 1 to the power, it becomes 2. Divide the 6 by 2. 3. 2 is the new power. 3x squared. All right. Questions about this? So I envision, again, just making them straightforward. 0 to 10. 6. 10 being impossible. No, I don't want to influence you. I'm sorry. 6. We have a 6. That I completely apologize. But you know that that's a very bad thing. I want you all, as teachers, to know that was horrible. All right, that's just bad teaching. If it's a 6 to him, it's a 6, and that is completely valid. I'm very sorry. I'm very, 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 very sorry. That's like one of the worst moments I've had ever in the classroom. I apologize. No, I apologize. That's terrible. No, it's not his fault. No, it's not his fault. It's my fault. 6 it is. Other numbers. This.
10 being hard?
10 being impossible. 12. And that's completely valid. I have no problem with that. Okay. Again, if you run into any problems, let me know. Okay. Yeah, I hope so. right? So again, shell method, rotating. Here's what I'm going to do, and this is off the record, I guess. I'm just going to go through these and I'm going to say which ones look nice, which of these pictures look great. Right? I like them. And there's some in the book. I don't know what section they are, where it says you would use whatever method you like, right? And it may be these. Right, so 27 through 32 test questions I like. Let R be the region bounded by the following curves. The question won't be exactly the same, but I like these. So let S be the solid generated by when R is revolved about the given axis. If possible, find the volume of S by both the disk / washer and shell methods. Let's just be on the record by saying that some of these will be test questions. I'm asking some of these exactly. And then we have the book to know what page number it is. It's not really a big deal. It's 6/5, 27 through 32. Right, and let's go ahead and make it 21 through 32. But the ones that you can do both, I like. Okay. So,
Did you say 6/5?
I think it is. Oh, it's 6/4. I'm sorry. It's 6/4. Thank you. Because obviously these are regions in which you can do both of them probably. And so those are the ones that I like if you've been paying attention. So hold me to that.
I have a difficult time visualizing the picture of the rotation.
That's why I'm giving it to you.
Okay.
I'm giving. Oh, no. So I'm gonna pick these, and then I'm gonna create the picture. Oh yeah, I'm giving the picture. And again, that's just being real, right? It's just being real. We all have access now to graphing features. It would be different if it was 1945. This is not an insult to any of my colleagues, but 1945, where someone would just give this, and then you would have to figure it out. Well, we can all get pictures to this, so why don't I just give it to you, okay? Other questions about what I'm asking, or anything about rotating volumes? I'm asking you to find length of curves, okay? So we ended last time with this. We did number 5 last time. Let's go ahead and do number 8. All right, the length of the curve. This one. Let's see. And the question, of course, is, and we'll remind ourselves about the length of the curve. It's called arc length, okay? The length of the arc. And last time we said on A to B, if F is continuous, then the length of the curve is this thing. So here's what I'm going to do, okay? I'm going to say, write an integral that represents the length of the curve, and for an extra however many points, find the length. Okay. So we're going to find the length for this one, for the one that we did exactly. You'll see the obscene amount of algebra that you'll need in order to do it. I'm not overly interested in you doing that algebra, but I will give extra points for it. Okay. I think we have it ready to paste. Here it is. Here's the function. There's f of x. We'll take a derivative of this, square it, add 1, put it under the square root, and we're going to pray that that's something that looks like we can integrate it. Okay, and that means we need to find an antiderivative. And again, the only antiderivative tools we have at this point is the substitution rule. Right? So when we do this, we're going to hope that we can substitute and do this effectively. F of x is equal to 1/3 x to the 3/2 minus x to the 1/2. F prime of x is equal to the power down. Now we're taking the derivative, right? 1/2 x to the 1/2 indeed. Minus 1/2 x to the minus 1/2. This one, you get this one's slick. Take questions about the derivative. Bring the 3/2 down. 1/3 times 3/2, so 3's cancel. 1/2 x to the 1/2 minus 1 is negative 1/2. F prime of x squared. It's all of this squared, and we're going to have to square it. I have to FOIL it out. When you FOIL it out, it's equal to 1/4 x minus 2 times this, so that's minus 1/2, plus 1/4 x to the minus 1. So if you were to FOIL this out, multiply this times itself, you get this. Questions about that? 1 plus f prime of x squared. It's this plus 1, and then it's 1/4 x, and again it's plus 1/2, and then plus 1/4 x to the minus 1. Okay. And now we need to take the square root of this. All right. So the integral from 4 to 16 of the square root of 1/4 x plus 1/2 plus 1/4 x to the minus first. I'm probably going to be giving full credit for that, okay?
Where did the 1 at the beginning, 1 plus?
Right, because 1 minus 1/2 is 1/2.
Oh, this
Right, because if I add 1 to this, then that minus 1/2 becomes a plus 1/2.
I don't think I'm changing.
Yeah. So again, I'll ask a question, say, write an integral that represents the length, and for however many extra points, actually do this, right? The problem I have with this, of course, is that it requires some math magic, right? We need to see that this is a perfect square. This is a perfect square. So that the remark is this, that, we'll put it in red, that 1/4 x plus 1/2 plus 1/4 x to the minus 1 is actually what squared? What do we see? You see it? And that's precisely why I'm not asking you to do it, right? Because, I mean, it's a little ridiculous to somehow expect you to know this just by looking at it. Okay. So that's the remark. And so the point is that the one that I give, you'll be able to just write the integral, get full credit. But then if you can see, if you have the clairvoyance, right, to see that the thing I'm going to give you is a perfect square, then for that I'll give you 2 more points for that. Okay.
Is that x to the negative 1/2?
It is x to the negative 1. And you need that, right? Because
Yeah.
when you square, you multiply by the 2 and it gives you a minus 1. Right? So it almost tells you what you need to have. And you can verify this, right? If you FOIL this out, you will get that. And so now this integral becomes doable. It's the integral from 4 to 16 of the square root of something squared, 1/2 x to the 1/2 plus 1/2 x to the minus 1/2 all squared. And then the square and the square root cancel. And then this just becomes a problem using the power rule. Please, sir.
Can you scroll in a second?
Say it again.
I have a question about something higher.
Oh, absolutely.
I know you kind of just said this, but when you added 1, how did that?
So if I add 1 to the, thank you for your question. If I add 1 to this, right, then the 1 interacts with the minus 1/2.
Oh, okay.
1 minus
I
1/2.
understand that, yeah.
Is that okay?
Thoroughly.
Okay. What'd you say?
I said thoroughly.
Oh, no, no worries, yeah.
Well, why would you have to add?
Only because, yeah, it's a great question, only because the formula dictates it.
Oh, okay.
Right, so it's 1 plus f prime of x squared, yeah. So, and listen, and here's what people do, and I don't have a problem with it. People, I'm going to say, you know, use the Arclength formula, and people just rush everything into the formula, right? But I'm addicted to accuracy, and I know that if I do it this way, it's really difficult for me to get it wrong. If I just piece by piece, just put it all together, and then put it under the square root. But, I mean, what we're used to doing is somehow just putting it all in there at one time, right? So it's just a matter of taste. So then, this becomes about a fundamental thing of calculus, 1/2 times. Now what I'm going to do here is I'm going to take this 1/2, and I'm going to add 1 to it. That makes it 3/2, and then I'm going to flip it, and it makes it 2/3. And when we talked about x to the 3/2, right? You add 1 to it, that's 5/2. And you divide by it, that's 2/5. And that's how we get that 2/5 you wrote me about. So it's 1/2 times 2/3 x to the 3/2. And again, you got to get good at this, okay? Everybody. Plus 1/2 times 2x to the 1/2. Evaluated from 4 to 16. And I know that's too fast. I know. I'm doing that on purpose because you have to come along with me. The grand challenge for all of us all teachers is we have a benchmark. We have a place we have to get material-wise, but the audience sometimes may not, may have a background in which it's hard to get there. And again, you're going to have this problem as teachers. Trying to find a middle ground, well, we have to get to this material versus, my class may not have the background to get to this material, right? But there's a middle ground, right? So when I say you have to catch up, this you have to do, okay? Now, we may not get all the way to the end of the material, but the material you do see, you'll learn it pretty well. That's all I can guarantee. 1/3 x to the 3/2 plus x to the 1/2 from 4 to 16, plug in 4, 16 and ended. 16 and 4 and ended. 1/3 16 to the 3/2 plus 16 to the 1/2 minus 1/3 4 to the 3/2 minus 4 to the 1/2. Simplify as you like. Now, I think that's actually a pretty number.
So if we leave it like that, you're good? We don't
Oh, yeah,
have
that's
to do
fine.
all the-
Yeah, you don't have to, yeah.
do all that.
Yeah, it doesn't serve any purpose to go ahead and do all of that by hand. Right? So any questions about what I'm asking for this one? Again, I'll be asking about this, but if you can go ahead and recognize some things, feel free to do so. Anything else about Arclength? Or maybe there's some extra credit here. So, no, maybe not. Any of these like absurd? Oh, we just did an absurd one. So, look 11 through 20. Look at the problem. Arclength by calculator. That's what we're talking about. The real functions that we want to know the length of, we just cannot do by hand, right? And this is like one of the few sections in the whole book where it just says you're going to have to get out a calculator and figure it out. Okay.
So did we determine we're not doing calculation for the test, but you also need a picture?
Yeah, that's right.
Or
That's what we
that's
yeah.
what we came to.
That is what we've come to. Okay, questions about Arclength? All right, here's the last thing we'll talk about. Some physical applications. Density and mass. Okay, so here's where we have to be paying attention to units. We'll be asking about the mass or the density. I'll give you the density and ask for the mass, okay, something like that. Okay. So mass is equal to density times volume. And I usually don't remember it this way. I usually remember it in terms of density, right? Something dense.
M over V.
Right, density is mass over volume. So, but obviously this is equivalent, right? So the more dense something is, the more mass it is per unit of volume. Okay, that means that mass is density times volume. Okay, so
It's funny that you're doing this too, because I'm in physics, chem, and biology, and I've done it in all of my three other.
that's interesting.
Yeah.
And how have they been different?
One of my teachers wasn't good at teaching it.
Okay.
The other ones
Well,
already taught it.
no pressure for me at all. Yeah, that's great. Okay.
Hey, I took you for the second time, so let's.
That's true. Okay. So here we have this bar, one dimension. Okay. So roughly, it's very thin from A to B, and the change in shading means that the density varies. Right. So the density varies, and so the question is, what is the mass? Okay. So if the density varies, at least from A to B, we'll break it into pieces, and we'll mark that at least on a small subinterval. And I'll do a picture here. Okay. So.
What, there's one object where the density varies on it?
That's right. So I'll take this and I'll put it here. All right. So here the density varies, but because of continuity, right? This is a continuous medium. At least the density here is roughly constant. And so we can figure it out. And the density here is roughly constant if the interval is taken small enough. Right? And similarly here, right? And so all we need to do, so when the density is constant, then we can figure out the mass, right? Pretty easily, right? So hopefully you see that we're breaking up the interval A to B into pieces. Right? And again, beating a dead dog at this point. I'm sorry, a horse? Beating a dead horse. I'm sorry. I said a dead dog last class, and they almost killed me in that class. You got to beat a dead horse, not a dead dog. I apologize. I've been saying the wrong things today. Okay. So the thing to remark is that on each subinterval, the mass, right, is equal to the density times the length of your subinterval. That's roughly the mass. Okay. And of course, we need to add up all of those things. And so, not shockingly, if I give you a function that represents the density, then you get the mass by integrating. Right. That is the lesson. So suppose a thin bar of wire is represented by a line segment on the interval A to B with a density function rho, and the units are mass per length, then the mass of the object is just the interval. Okay. Question number 11. I'm going to give you a function. And again, as you can see that, well, one, the first thing is that this is one of the major applications of the integral to physics, okay? And then now I'm wondering, did they mention the integral in these other contexts? In chemistry, no. They didn't say anything about it. So they mentioned the derivative, okay. Is the density always constant in these objects?
Yeah, it's an intensive property because it doesn't matter how much of something you have, the density is always the same.
The density is always the same, okay. So, do we have any objects where the density varies? Think of an object.
Yeah, well, that's what I'm going to ask you.
Yeah. What object exists where the density varies throughout? I guess we'll just have to stop. We're not going to do anything until we can go. Otherwise, it's pointless to do it.
It
Right.
has to be made of different materials.
Yeah.
Of course, that's fine.
Is that?
A cell,
Say it again.
a cell,
A cell. Wow, but
biology, and you need to figure out density.
throughout the cell? Yeah. Well, that's such a small level, but that's true. Can we think of a bigger object where the density varies throughout? person, okay, where are we more dense? Right, yeah. But certainly lots of things, right? Cars are dense in different places, obviously. So, yeah. So, okay. I'll take this one. Let's go ahead and take that. So, was there? Okay. But don't we have some engineers in here? No. I think we're gonna have some future engineers. No one wants to be an engineer in this place.
What kind of?
Any type of engineer. No, no, you're shaking violently no. Okay. All right.
This is question 11. Stephanie.
Say it again?
This is question 11.
Yeah, question 11. So here's question 11. Question 11, I'm going to say, it's going to be in a couple of parts because there are a number of applications, okay? So it's going to say, the density of an object is given by blah, find the mass, okay? It's also going to say you're lifting a bucket of water, however many feet, what's the work done in lifting that bucket over, some ledge or something like this, okay? We'll get to that in just a moment. But this is the crucial observation. So, and I guess I should reiterate the same procedure over and over and over again in terms of how the integral arises in terms of an application. We have some fundamental physics principle, right? That's true when things are constant, but then when things are different along an interval, somehow the integral pops up, okay? And that's why it's important that whenever we want to find the total amount of whatever, the total mass, the total work, the total force, the total anything, then we're talking about adding up things, right? And if we live in a continuous medium, then we're adding up smaller and smaller pieces, right? And that, of course, means that we're going to be integrating. Right? That's why the integral is important. And, this may be blasphemous, but the integral is the center of calculus. Right? Now, this whole time I've been saying that the integral is about two things. It's about the derivative and it's about the integral. And obviously the derivative has its applications, but it's the integral that's important. It's the integral that fueled all of this here, because people need to know what's the total this, what's the total that. And these problems are difficult. And they were always difficult until we were able to connect the integral to the what? Begins with an A. This is all difficult, right, until we were able to connect the integral to the antiderivative. And that's why antiderivatives are important, and that's why derivatives are important in this context. Okay. Questions about that? A thin 2-meter bar represented on the interval 0 to 2 is made of an alloy whose density in units of kilograms per meter is given by 1 plus x squared. What's the mass? So I'm just going to take one of these, throw them on the test, just to make sure you're breathing, okay? And the real hope, and I'm just being too honest today, the real hope is that literally I've done my job. If, 5 years from now, someone asks you, or you encounter, what is the total mass, what is the total whatever, and you say, oh, that might be an integral. If you do that 5 years from now, no, I mean, if you can do that, but let me just say, if some percentage of you can do that years from now, then I am a happy person. Okay, so if you get that concept, or let's say this way, if you see that it is an integral, you won't be surprised. You won't be surprised that the answer is actually an integral. When you're reading a paper and someone says, we need the total blah, and they say, it's given by this, and it's an integral, you should be like, oh, obviously, yeah, it's an integral. I mean, yeah, exactly, it's an integral, right? So. I'll take that. I'll take it. I'll take it. All right. So again, I think it's a gimme. I hope I'm just giving it away. I hope.
Then the question, what is the mass?
That is, what is the math? That's
Okay,
right.
making sure.
Let's see if I can make it smaller. I don't think that I can. Yeah. So again, this will be an exercise in two things: whether you know the relationship between mass and density when the density varies, and can you integrate? X plus 1/3 x to the third evaluated from 0 to 2. 14 over 3. I think it's 14 over 3. 2 plus 1/3 times 2 to the third minus 0 plus 1/3 0 to the third. It's 2 plus 8 over 3. You can leave it like that, but that's 6 over 3. Common denominator plus 8 over 3, 14 over 3. I'll take questions. So, I mean, this is not that difficult. Everyone knows how to integrate. You just have to know the relationship. What are the units here? 14 over 3 kilograms, right? So
What's kg every time?
kilograms per meter. Per meter. And so in one dimension, the volume is in one dimension. Okay, so it's kilograms per meter. Right, so it's just kilograms, the answer. Okay. Work. Work is force times distance. So work is the amount of force you need to apply along a certain distance. When the force is constant, then you just merely need to take the amount of force times the distance, obviously. But of course, the force for us is going to vary. Can you think of that example where you require less force, right? The classic example is when you're pulling up something, right? You're standing on a ledge and you're pulling up a bucket. It's less work, you know, maybe at the end than it is at the beginning. Why? Right? So you have a bucket and you're pulling up a chain. You're using a chain to pull up the bucket. Why is it less work at the end than at the beginning? Because of what? What's the bucket's closer, but the weight of the bucket never changed. It has something to do with the distance is different. That's right.
Gravity.
Gravity is the same. Gravity's constant. Right? It's slick. It's slick. It's a slick question. I'm not trying to trick you. Go ahead.
Pulling less though.
You're pulling less chain. It's all in the chain. Right? It's less chain. Okay. So here, this is in one dimension going that way. Usually in the problems I'm going to ask, you're going to be pulling something up where gravity is affecting things. Okay. So units, right? So a newton is the force required. You remember that guy, by the way? A newton is the force required to give a 1 kilogram mass an acceleration of 1 meters per second squared. Right? So a newton is the force required to give a 1 kilogram mass an acceleration of 1 meters per second squared. Okay. A joule is 1 newton meter. Okay. So the only thing to remember is that these are the units for force, and these are the units for work. Right. The work done, so a joule is 1 newton meter, the work done by a 1 newton force over a distance of 1 meter. Okay. So I am not a physicist, but those are the definitions. As, again, calculus enters the picture when the force changes, right? When you have to apply different forces at different times. Not that big of a deal, right? Over an interval, A to B, where you apply different forces, will break A to B into different pieces, and observe that on such a small piece, right, when you're pulling up the rope, the bucket, on a small time interval, the force is constant. Right? And therefore, you need to add up all of those forces. And here is the definition that force that work is the integral of the force. So I'll give you a force function, and then, well, I'll give you a context, the problem, and you'll have to figure out the work done in that problem. Questions about that? So I'm giving you this in question 11. Right? So question 11 will be about work and about mass. Okay. Let's do an example. All right, so suppose, let's start with, so lifting problems. Another common work problem arises when the motion is vertical and the force is gravitational force. The gravitational force exerted on an object with mass of m is F equals mg, right? So mass times acceleration, where g is gravity, is the acceleration due to gravity near the Earth's surface. The work in joules required to lift an object of mass m, a vertical distance of y meters, is force times distance, which is just the mass times the gravity times the distance y. Now, of course, the problem becomes interesting when the object lifted is a body of water, a rope, or a chain. In these situations, different parts of the object are lifted different distances, so integration is necessary. And here's a typical situation, and here's what we'll do, and this is what I'll ask. Suppose a fluid such as the water is pumped out of a tank to a height h above the bottom of the tank. How much work is required, assuming the tank is full of water? So here's the picture. The picture's here. You need to lift all this water out. You need to lift all this water out. Okay. So that's one piece that you're lifting out. You have to lift out all of it. Okay. And so, but that's only one piece. You need to lift out this piece, this piece, this piece, all of it, right? Hope we can see it again. This is going to be an integral. Okay. What is this piece? Well, the way that you get the volume of this piece, right, is you need to find the area of whatever this would be, right, times this delta y, and then, of course, times gravity, and then times the density of the object. Okay. So, density, the distance, the area, and gravity all play a role there. So water from different levels of the tank is lifted at different vertical distances. Water from the same horizontal plane is lifted the same distance, requiring the same amount of work. And a volume V of water has mass rho times V, where rho is 1 gram per centimeter cubed, which is 1,000 kilograms per meter cubed, which is the density of water, right? So I have to give you that. I have to give you the density of whatever the substance is, right? So that you break up the y-axis into n pieces, right? And then you try and calculate the force on each piece that you have. Right? Let's see how we get that. So the force is, well, I should say the force on the kth layer. How do we get that as the force? So the force is mass times gravity. They're claiming this is the mass. The mass of it is the area times the width times the density. That's the mass. All right, so this whole thing here is the mass. Let me go ahead and take this. And we'll annotate it. All right, so for this problem here, we're making the remark that the force here is simply, we'll leave it like with an arrow, that this is simply here, mass times gravity. So this is just force equals m times g, and it just so happens that in order to get the mass of the whole thing, then you need the area, A, times delta y, times the density. That's the mass. Because it's just volume times the density. We said that earlier. Right? So maybe we should put that in first. The mass is rho times V, but in this case, I should have closed that off. That's equal to rho, but then the volume is simply the area times the width. Right, and they make that remark here. Okay. What's the point? Right. The point is this. Now that's just one piece, but then we're going to add them all up again. Right? So the cross-sectional area of the cape layer is just the area there, and is determined, of course, by the shape of the tank. And the solution depends on how you find what the area is. Okay, so the work done is given by this. Right? So when you're lifting stuff, and we'll do some examples in just a second, then it's usually going to follow this formula, right? So draw a y-axis in the vertical direction and choose a convenient origin. Assume the interval a to b corresponds to the vertical movement. And then for each y between a and b, find the area, and then you need to find the distance you need to take that slice, and then you need to add all of those things up. I'm going to take this too. And then we'll do an example of something that I will probably ask. Okay. Questions about any of this? So let's be good. All right, so we'll need arrows. This. This is just density. And that is given. Or you have to find it. Gravity. This is the area of a section that you need to lift out. This is the distance remaining to lift this section, and this is the width of the section. Of course, I don't need to put an arrow by the integral, of course, right? The integral is you add up all of the, you just add them all up.
I can't see the formula.
Oh, okay, so now let me make it bigger now that I've done that. So it's rho, G, A, the distance, and the width. Right? So it's rho, you need, so it's just these constants on the outside, okay? So these are coming out of the integral, they're constant, right? So I'm not gonna have you lifting, something out of some mixture of things where the density of the liquid is variable, okay? So rho and G are constant as these things that are changing. Okay. Questions about any of these things? Okay. All right. Let's do an example. So how much work is needed to pump all the water out of a cylindrical tank with a height of 10 meters and a radius of 5 meters? The water is pumped to an outflow pipe 15 meters above the bottom of the tank. And so let's take a look at the picture. So we're lifting, so we put this picture here. So on the y-axis, we just put the cylindrical thing here, okay? And so then we're going to pick a y, and then we're going to lift this out. Okay? Let's write the integral for this one. So, and also, we need, let's write it, it's the integral from A to B of rho G A, the distance I need to bring that piece and the width of it. Rho and G are given. Literally this we're looking for. Right? So now when I pick a y here, what is the area of this, right? So it's just, and here's where it's crucial that you see that the area is pi r squared. Now why is it pi r squared? Because it's a cylinder, right? So capital A depends completely on the object I give you, right? So you literally have to say to yourself, if I slice a cylinder, right, sideways, what is the object that I get? And you get a circle. It's just that simple. That's why it's pi r squared. Okay, so it's capital A of y is simply pi times 5 squared. And in this case, it does not depend on y, but for us, it's going to depend on y. Right? Because if I give you something else, like a cone, right, then it's obviously going to depend on y. We'll do something like that in a second. So the area is 25 pi. Right? What distance do I need it to drag it out? This is level y. What distance takes me out? The whole thing's 15. I'm y units. The distance left to drag it out is 15 minus y. Right? So you pick a y, and you need to pull it the rest of the way. Right? So it's 15 minus y. This is about that. So now, thank you. Great question. I need now that I find the area, and I have the area times the width, I now have the volume of this object, okay? Now I need to pull it out a distance, okay? And so the distance is given by where I've decided to look at my particular object. And here, it's at level y. Okay, and I need, the whole distance is 15. Okay, the whole distance is 15, and I need to pull this out, whatever's left. Well, if the whole thing's 15, this is y, then the remaining is 15 minus y.
What is that? 15? What unit?
So let's look at the context. I'm sorry, what is the units of 15?
The unit, the measurement unit.
Right. So I think we're in, is it meters, feet?
Okay. All right. I
Something
think
like that.
it's meters.
I think it's meters too. Let's look back at the problem.
I mean, I don't need to know. I just.
Okay. All right, so again,
Yeah.
so the height is 10 and the radius is 5. So right, so it's pumped to an outflow pipe that is 15 meters above. Okay. So that now d of y is 15 minus y. And the game is over. And then you integrate. Okay. Now the only difficulty, and we'll do some of these, the only difficulty comes from when a depends on y, d is always going to depend on y. Okay. But then it just becomes a pretty simple integral. The real problem is formulating the problem, drawing the picture, and formulating the problem.
Can we go back to the picture?
Thank you.
So it says a tank top is 10.
Right, because so what they're going to, so again, it's all in the context of the problem. What they want to do is they want to pull the word out and then push it into some other thing that's 15 above the bottom.
So how do you know where the water level is? If the bottom is 0,
Yes.
the tank top is 10 right there,
Right.
and that's that, so the water level would be 5?
No, so they have a tank that's full of water and it's 10
Right.
meters high.
Right,
Here it is.
right,
Okay. Now we're going to take all the water out and put it into this outflow.
right.
Okay. So the way that we do that is we go to any level and start taking it out and see what happens to a particular level, and then do that for all of them. But your question is,
How do we know what that level, what is y at the water level right there, at the blue? Do we not need that?
wait, this here?
Yeah,
Oh, so we pick a typical one.
okay.
So we pick it at level y to see what happens at y,
Okay,
to see what happens in general.
okay.
I see what you mean. What is it? If the total is 15, what's the level at y? You don't know, right?
No, we call it y. And the reason is because we want to figure out a general formula for any particular, so I could do this, right? So I could say, well, what is it at 1? What is it at 2? What is it at 3? And then add them all up. But instead, I just say, what is it at y?
Okay.
Yeah.
Okay.
Is that okay?
Yes, yeah, I thought we were trying to figure out what y was at that.
Oh, no, we're not trying to figure out what y is. No. We're not solving for y here. No. So the game plan again is, in order to get an idea of how to take all of it out, we take one specific slice and and call it y and see what happens to that particular slice. Remark that particular slice is not special, right? And therefore we can add them all up. That's the game plan. Again, questions making the class much better. Rho times g, I don't really care about these. Okay. Integral from, I'm a mathematician. Okay. So where's y varying? Y goes from what to what? 0 to 10. 0 to 10, that's right. So y goes from 0 to 10 of 25 pi. That's about to come out too. Times 15 minus y dy.
Where did you get 10? I'm sorry.
Thank you. So where does the water level vary from? And now I'm going to vary y. Y goes from the very bottom, I need all of this, to the very top. All right, I'm taking all of that out. So it's 25 pi times those other constants. And then yon. Is that 50? No, not 50. A 100. I think it's 100. So 2,500 pi row G. So 15y minus 1/2 y squared from 0 to 10, 25 pi row G times 150. 10 squared is 100 over 2 is 50. 2500 pi G. Questions on that? I have to get some math homework on these. Okay. About this. Let's go ahead and do some more.
What did you get the minus 1/2 y squared?
So, right, so the power here is 1, right? Add 1 to it, divide by it, yeah, it does get you every time. You gotta get sharp at that. Right? Add 1 to it, divide by it, that's the new power. Practice. All right, so 25. I had 100. They have 1,000.
For P?
Oh, for if that's row, that's right. So then, okay. Okay, so that's a nice one. Let's do some exercises. All right, so non-Jew 16, I'll ask something like that, okay? Find the mass of the following thin bars for the given density function, just integrating, right? So again, I think that is giving away points, I hope, right? The question, of course, is how difficult will the integral be, right? And again, any of those are possible, basically 9 through 13. The other ones are piecewise and can be done. Let's see if we can find one that is fun. Is there, let's see here, no?
I remember that swimming pool.
The swimming pool, oh.
That's the physics.
That's, oh, is it a physics one? Okay.
Tutors can never help me figure out.
Oh, that's right. Let's see if there's one. Lifting, emptying a cylindrical tank. How much work is required? Yeah, so I may ask something like 24. They don't have any of these ones with the buckets here. I guess not. So a spherical tank. Let's do the one with the cone. Emptying a conical tank.
You have exactly 10 minutes.
Okay. Okay. We have a deal. We have a deal. Well, you know what happens, of course, that if I don't, what happens?
Then we
No. I might give it for extra credit. All right, so a water tank is shaped like an inverted cone with height 6 meters and base radius 1.5 meters. See this figure. If the tank is full, how much work is required to pump the water to the level of the top of the tank and out of the tank completely? Is it true that it takes half as much work to pump the water out of the tank when it is filled to half its depth as when it is full? And so if the tank is full, how much work is required? So let's go ahead and put this on an axis. Right, so we can do this. Second picture, so it seems like we want to do something like this, okay? so then we're going to pick a y here. The question, of course, is, oh, this would be great, actually. And so the point is now, what is that object? What is that object? All right, so again, it's the integral from, and we're pulling it all, right? So it's 0 to 6, right? It's the integral from 0 to 6 of, and now we need rho, g, a, and the distance we're pulling it. Now, because this is a cone and not a cylinder, now the circles are getting bigger, right? As a matter of fact, you're doing more work, it seems like. Or at least it's, the thing that you're pulling out is getting bigger the higher you go up. Okay. So it's equal to rho times g, the integral from 0 to 6 of a of y, d of y, dy. And the question is, what in the world is a of y? So now when we cut this across, what is it? It's a what? When we take a slice and then face it to us, it looks like a circle for sure. So it's pi times some radius squared. Now what is it? How does that depend on y?
That'd be x.
We're moving, we're doing it in terms of the letter y.
Okay.
So how do we know?
Radius is
1.5 minus.
No, that's all the way at the top. But what is it here?
Is that, are you saying the middle?
1.5 minus y or?
Yeah, what is the radius at that?
Yeah, what is the radius at a particular y? That's right. And it depends on y.
Would it be something like 1.5 minus y?
Something like that, right? Maybe. Right, and so here's the real issue, right? So we need to find the radius here. So we need to find this distance, right? We need to find this distance here. We know that's y, right? So here is the remark. I'm going to put it in blue, and I think I'm going to need to go ahead and get this picture again. I want this picture. Ooh, let's put an R for sure. That's brutal. With a Mac. And so here's just a little slickness here. Right, so I'm gonna make it clear. All right. So we wanted to know what happens at distance y at this point, right? Now we need to relate it to 1.5 and 6, right? So let's go ahead and make a remark. Tell me how 1.5, 6, y, and this number are related.
They're like equal ratio.
It begins with an S. Those triangles are similar. Those triangles are similar. And so this triangle here, oh, well, I need this, right? This triangle here, and the one that I just drew initially are similar triangles. Okay. Questions about that? And so what does that mean? That means that y over, what is this radius? Do we know that? Is that not what we're looking for?
Yes.
Okay, so we're going to call it r is equal to what?
6 over
6 over 1.5. So y over r is equal to, that's a nice pretty 4, and then r is equal to y over 4, and so it's y over 4. Okay. that's how you do the cone ones, right? So again, the difficulty is only in the object that I give you, right? The cylinder was easy. The cone, you had to make this observation, right? I don't foresee giving you an object that's like out of control. It's y over 4. By the remark. What distance do I need to carry it? 6 minus y. It's the integral from 0 to 6 of rho times g of pi times y over 4 squared times 6 minus y. I'll take questions about this. About any of the similarity or anything like this. Now, if I was to give this question on the exam, right? If I was to give something like this, and you had never seen it before, then I would have obviously made this a hint, because it's not obvious what to do. Okay. 0 to 10. 100. Yeah, I know these. Yeah, these. I think these would be the hardest ones. But trust, I'm not gonna give you something ridiculous.
I mean, at some point we have to learn.
Yeah, that's right. That's when you go to my math lab and you slug through it. You scoff at my math lab, sir.
Oh, man.
You do. Yeah. Yes, you were. It's okay.
It's pretty bad. My math lab's not really helpful.
It's not helpful.
Not now. It was Calc 1 and everything before that,
But now it's just in the way.
They skip steps and things like that, and it's hard to figure out.
Okay. All right. Right on time. Right on time. All right. What? Yeah, 11:15. Let's now review. Let's get all the test questions together, and then we'll be good.
Is this it for?
That's it.
Did you do part B?
Part B? Oh no, I didn't do part B. I'm not even going to ask part B.
That was for extra credit.
Oh, you want to make part B extra credit?
Now I heard
So let's see what part B says. Is it true that it takes half as much work to pump the water out of the tank when it is filled to half its depth as when it is full? Oh, okay. So what does that mean? That means that if it was only filled up to 3 meters, and you look at the work to pull out all 3 of those meters the whole way, is that half of, is it just A? What happened in A? Yeah, I think, so if, is the integral from 0 to 3, half of the integral from 0 to 6, well, you get half the answer. Right. So, I think it's no, right? I think it's pretty obviously no.
We don't get extra credit.
Yes.
I can give you other extra credit. So, yeah, yeah. I need to think about. I haven't been getting a lot of extra credit really.
Make up for it with that problem.
Say it again.
Make up for it with that problem.
With that problem, oh, I know, but I need to be way more creative than that, right? Oh, if I'm gonna, let's get to it. Let's do something like this. Let's do that. So, number 1, what's number 1? Thank you. define the interval. 2. People are searching through their notes. So we use, is that right endpoint, left endpoint method? Is that right? Okay, so it's right endpoint, left endpoint approximation. Okay, and then you're supposed to have these down.
I did.
Let's go.
Oh,
What are they?
sorry.
I'm literally asking what they are.
There you go. Question 3, define the length of arrow type of
Okay.
word.
See, you're ready to leave, but then you won't help us. Did I?
Oh.
Count.
Fail.
Calculus. There we go.
Number 4, it was using the substitution.
I thought that was 5.
No, well, 4 and 5.
Oh, basic antiderivatives. Okay. Okay, and then 6. What is it?
Find the only function satisfying.
Oh, okay, so velocity, position / initial value problems. So, okay. What do we have? Okay, fine. Okay. Is that not it? Find the area between 2 curves. 8. Are we then rotating or no? You have what? Uh-oh. Did we miss something?
Number 8, find the area between 2.
Oh.
So they won't
So
calculate.
7
What's that?
says find the only function satisfying the
Yeah,
equation.
yeah.
That goes through.
But that's 6.
No, no, no.
But that's what I mean to be 6.
I think we should skip and go on. Maybe we.
Oh, now I reserve the right that if I find something that I missed, it's going in there. So it's better to get it out right now.
I think you should be here.
What? Okay.
Here's number 4 and here's number 5. Okay?
4. No, 4 is just 4 is something like this. Right. That's 4. But these are basic
And then
antiderivatives.
that's 5.
Yes.
Okay?
Yeah.
So then, that would be 6 right here.
What's 6? Yes, that's what I have.
Okay.
Yeah. And then 7.
7
Yeah.
would be this.
7
And
is.
then 8 would be this.
Oh no. I'm sorry. 6 and 7 are identical.
You know what?
6 and 7 are identical. 6 and 7 are the same.
So that is 7.
Yes, so this is 7, that's right. So when I say find the only function, right, that's an initial value problem. Find the only function. So 6 and 7 are the same. Find the area between 2 curves, and then after that, are we rotating?
Find the volume.
Find the volume, okay. Yeah, that's by rotation is fine. And then, is it just arc length?
No, I think it would be the distance from well,
Yeah, that's the length of a curve, right? Yeah, the length of a curve. Okay, so then there's arc length. And then today's stuff. I thought we were on problem 11. Oh, because of that mix up. Okay. Yeah, and said they were different. Okay, perfect. So then, oh, so a nice tidy 10. And so then work and mass problems. Perfect. That looks glorious, doesn't it? Just fantastic. Let's bring it here.
How would you answer number one?
Tell me what you would say.
I really have no idea.
Okay.
Oh, yeah,
And so,
I had to look that up.
you had to look it up? Okay.
Well, yeah.
Well, there are a number of different things to say about that. One, if you don't know number one, I should just fail you. So, because we've been talking about the integral the whole time. Okay. So, now some of you have me before. I'm one of the easiest graders. Okay. So, if you just tell me how we came up with the integral, what is it? You know, there's some fundamental things. There's like 4 fundamental things in order to create it, right? So what do we need to do? What do we need to start? You need a function, and the function has to be continuous. Okay, yeah, that's right. Oh, it can be. You're ready to go. It doesn't have to be non-negative, but so you need a continuous function on
Closed interval A, B, A, comma B.
on the interval a to b. Okay, and then what are we going to do with it?
Split it into
You break up a to b into n pieces, and then and you do the height, the width, yeah. The width is already done. So you break it into n equal pieces, that's the width. And then the height is, you pick a place in each sub-interval where you want the height to be. And then what? You multiply all the heights and widths, and then you add them up, and then you take the limit. This is what we've been doing the whole time. We did that actually 2 times today, right? We were talking about work and mass. You broke up the interval a to b into n pieces, and then you added everything up. Write that or whatever's in the book. Okay. But as you know, if you go to the website, if you go to Blackboard, there's a PDF for you where I've written out the definition. Okay. Which problem worries us the most? 10. Reasonable. And that always happens. The last problem on the exam is usually the one that worries us the most because we haven't practiced it yet.
I think it's
7
7 and 8.
and 8?
Yeah.
7, I'm going to give you
okay.
2 curves.
8.
Okay. Okay, so 8, I'm going to give you some, not death? No way. No way. No way. Are you telling me? Okay, so 8, I'm going to give you a graph. And I'm going to say rotate this graph around an axis. What problems come up? Like you don't know where to start?
I don't even know. I'm just like,
Okay. Well, that's good. That's good. Okay, that's good. So yeah, we'll figure something out there. Okay. So, but that's practice. That's good. Other comments about these 10? The 10.
On 4, do you mean by basic, do you mean the trig identity?
Right. So when I say basic, 4 looks like this, and we're going to start reviewing for hardcore on Thursday. But 4, thank you for your question. When I say something like 4, literally, I need you to have these down cold. I mean, you've got to tell me what this is immediately. Right. These are just basic ones that I need to know that you know. What?
I just guessed and I was right.
It's the inverse sign. Okay, good. That's a good sign. That's the inverse sign. This is
Negative sign.
It can't be negative sin x, right?
it's sine x. It's sine
That's
x.
the question I have. When you use those, what's that stuff called? And I hate the whole class, but I got to explain it.
Oh, okay, think about it.
Yeah, I got it right here.
Yeah. Okay.
Yeah, when you're doing trig functions,
Yeah.
cosine is actually negative sin x, but if it's an antiderivative, it's just
Sine x. That's right.
Yeah, I figured it out after looking after so many problems. See, that doesn't make sense.
Okay, so again, and the important thing is to saying words what this means. I'm looking for a function whose derivative is cosine. I'm looking for the function so that when you take the derivative of it, you get cosine.
Okay, wait, going back again, this integral of cosine x dx
Yes.
should actually be negative sine x.
And what I'm saying to you is that what is the derivative of negative sine? What's the derivative of sine?
Derivative of sine is our cosine.
Perfect. What's the derivative of negative sine? It's negative cosine.
So
Right.
you say negative is positive.
All I'm saying is that the derivative of negative sine is negative cosine.
Okay.
So this can't be right. Because the derivative, whatever this is, the derivative of this has to be that. But the derivative of negative sine is negative cosine, not positive cosine. Right? So all you're doing is reversing. All you're doing is reversing the list.
I keep forgetting that.
That's what I'm asking for number 4. Okay.
We talked about that yesterday. Just adding the constant c.
Right.
When you're doing an anti.
Yes.
On number 7, when we're finding the area between two curves, do you want us to like do it with respect to x and y? Like,
Probably, yeah. Yeah. But that won't be that. Again, I'm giving you the picture, so it shouldn't be that. Other questions about these 10? We'll get to work on them on Thursday, hardcore. It's going to be okay.
I mean, it's cool. Like,
Yeah.
You know, I was working with like the first couple of them yesterday. This here is I put it on this one.
Yeah. Okay.
I mean, that's pretty self-explanatory.
Okay.
I'm okay with 7.
Okay.
When you get to like rotations and stuff like that, that's
Right.
I kind of just I won't say I zoned out, but
Yeah.
I kind of just you guys were walking through the forest and I took a left turn.
Right. Okay. I got you. Well, we need to review 7, 8, 9, and 10 then. I don't think 9's so bad either, but
No,
8 and 10 we'll have to review. Okay, that's good. Because
when you say state the fundamental theorem of calculus you want, is that another definition?
it is, and you can find it.
Where the heck is it?
That was given.
Oh.
They wanted to know the length from 4 to 16. That was given in the problem.
I was like, man.
Yeah.
So how much worse is it going to get through the semester after this?
It's all relative. It's all about what you prefer.
No, I really like it, but I mean, sometimes I just get frustrated.
Well, I mean, the next chapter is just all antiderivatives. There's just all these methods that you have to learn. Yeah.
Thank you.
See, but some people like that much better. Yeah.
I would-
So.
I mean, I like it. Don't get me wrong. I wish it like Calc 1 was like that for me. You know, it wasn't too bad at all.
Yeah.
Some of this, oof.
Yeah.
That's what I felt it was too. I feel like Calc 1 made like sense.
It didn't.
Okay.
I mean, not that, like when you're doing it, I'm like, okay, I feel like I did that. But then I get home and I'm like,
Right.
it's the same thing as physics is for me. Like, I just don't. Physics is worse though because it makes absolutely no sense.
Right.
So, oh my gosh.
That's
It's
funny.
just like, I don't understand what you don't get. I'm like, me neither.
Right.
Tell me what I don't understand. I have no idea, but I cannot reproduce those results. on
That's
that.
so funny.
And that's what scares
Hey,
me.
Dr. Weaver, are you a mentor here?
I am a mentor, absolutely.
Good, man. I was afraid to ask you. I need
No.
like I don't know how to say this. I need a new mentor.
Okay.
I think, and I don't know how to do it.
I think you just go to the registrar.
Really?
Yeah, and just tell them.
Yeah, there's a.
I think there's a form and everything, so get it done and that'll be good.
So you won't mind me?
Absolutely, it would be an honor, sir.
Because like I don't know what to like. You know, here's the thing. I got laid off from June, which I was so happy for, and I want to try to do a career change. I already have like 1 degree and kind of had another degree.
Okay.
I know it sounds weird, but
No, that's fine.
I'm seeking a 3rd degree in mathematics.
Okay.
I'm just thinking about that. Maybe to teach
Okay.
like middle school.
Yeah, okay,
Just
yeah.
to start off, you know.
Yeah.
But you know, at some point, I wouldn't mind. See, I don't really want to go back to corporate America, but that side of corporate America, which is math, might be different.
Right.
But you got to be very, very good.
Yeah.
Because I like to work alone. I don't like working in groups and stuff.
Yeah.
You know
I
what
got you. I got you.
I think math might allow it.
Yeah, right. No, I agree with that. Yeah. Yeah, well, we have a math ed program here.
Well, I'm in applied math right now.
Yeah, okay. Well, I mean, if you went into the teaching part, then you can do the...
Well, I'm going to do it differently since I got laid off. I'm a dislocated worker.
Okay.
And I can get the WIA
Okay.
to pay for this teaching certificate with the majority college.
Okay, very nice. Okay,
It's
good,
like a
good.
year from-
Okay, that's pretty cool. Okay, so you have a plan. That's good.
Of course.
Okay, that's good. Then you don't need me to mentor you. It seems like you have a plan.
Well, no,
So,
on the math part, you know what I mean?
Oh, I got you. Yeah, no, because it's going to be extremely difficult, but it is very doable. A math major is just not a joke.
Really?
But but
But I've heard that the hardest math is calculus, the calculus courses.
you can if you're logical, then you can get through a lot of the other stuff. Yeah.
Really?
Oh yeah. If you have the logic down, yeah. So what are you taking next semester? We'll have to talk about that.
Well, see, that's what I'm doing. I'm going to start hopefully that teaching. I got to pass that Gacy math content first.
Right. I was hearing about this. Right. Okay. So.
Good thing there's no calculus on it, really, you know.
Right. Yeah. That is a good thing.
But I've never had geometry at the college level.
Okay.